Hope you guys are having a better start to the week than I am. I'm ill, and my dog pulled me over this morning, so I feel not great. But we will push through and we'll survive. I hope you guys had some good lectures with Aline last week. We're continuing looking at infectious disease models. We've got this week and next week, basically. There's one more quiz at the end of next week, and then the final session will be a review session. Just a little bit of a heads up for that final review session, which I think is on the 4th of December. I can come up with stuff myself for that, but it would be really helpful for me if you could start thinking about things you would like for me to go over that you maybe want to have a little bit more explanation about or more practice about in advance of that. So maybe by around sort of next Wednesday of next week to maybe drop me an email if there are things that you would like me to focus on more. Yeah?
Can you put some of the exam that's gonna be in the final?
Yeah, we can go through some so what I'll do is I haven't started writing the exam yet, but I'll write the exam within the next week or so, and I'll write a practice exam as well for you guys, so you can have a practice exam. And we can talk through some of the practice problems, which will be very similar to the exam style questions as well. But definitely, yeah, if there are particular topics within, that you would like me to focus on, if you can drop me an email and let me know, and then I can try and tailor that session, because obviously we're not going to be able to cover the entire course and review everything in about 50 minutes, okay? So I'll try and tailor it to the things that most people want to focus on, okay? Okay, so today we're looking at vaccination. So far we've been thinking about how infectious diseases spread in different types of models. Last time with Aline, you looked at host heterogeneity, so if there's variation within the population. Now we're going to be thinking about vaccination. So today we're doing vaccination as one method of control, and on Wednesday we're going to be talking about non-pharmaceutical interventions, so things like social distancing, lockdowns, and so on. How do these feature in models, and how do they help us to control infectious diseases? Okay, so today we're going to go through, we've already talked briefly about the concept of herd immunity. We'll talk about that a bit more today in the context of vaccinations. And we'll talk about two different types of vaccination programs. One is if you have pediatric vaccination or vaccination of young children, and the other is targeted vaccinations, which builds on our ideas of host heterogeneity. Okay, so I'm going to start by a little bit of a history about vaccination and how they work. So, typically, we model infectious diseases to try to understand them, but also to make some sort of public health forecasts often, right? We want to use them to try to help us to better intervene and to understand where things are going and how we can try to control infectious diseases. So one of the real useful things that models can do is to help us to think about different scenarios about how, say, we apply an intervention, whether that's something like drug treatments or vaccines or lockdowns or masking, as I'm wearing now, and thinking about how these different scenarios might play out and might affect an epidemic. Okay, so there's quite a rich history of mathematical models informing vaccine programs. Okay. So vaccines are indeed one of the best tools that we have to combat infectious diseases. This is because they can both reduce disease, but also prevent onwards transmission. That's not always the case. We can have things called leaky vaccines, where individuals may be protected to a certain degree from severe disease, but then they can still transmit. And that has some interesting evolutionary implications, which we might get to at the end of the course. But there's different types of vaccines, and generally speaking, they reduce transmission and can reduce disease, but not always both of those two things. And they do this by stimulating an adaptive immune response. So as vertebrates, we have both innate immunity and adaptive immunity. And the adaptive immunity is what helps us to recognize and remember previous infections. So we detect antigens, so things like proteins on the surface of a virus, and we form antibodies which recognize those different types of antigens. Okay, so if you previously had measles, for example, you recognize the antigens on measles, and therefore you're protected from that in the future. We can also replicate that using vaccines, so we don't necessarily have to have a previous infection. So vaccines essentially leverage this particular component of the adaptive immune response. So what are we going to do today? Today we're going to be thinking about our SIR framework to explore how we can vaccinate populations and to prevent an epidemic using herd immunity. Okay, so the first vaccines, I mean, people have been thinking about the general idea of vaccination long before this, but really the first well-documented examples stem from the 18th century, where Edward Jenner, there's an institute called the Jenner Institute, which develops vaccines, which is named after him. So he was an English physician, and he wanted to try to protect or develop a vaccine against smallpox. So, back in those days, they didn't really understand what these things were necessarily. They just knew that there was, some contagion that people could get, and knew that cows would get a similar infection or have similar symptoms to humans would have. So he took a cowpox sore from a cow, I believe from a cow, and this is where the word vaccine comes from, incidentally, the Latin word for cow. So took this sore, mushed it up a little bit, and then injected it into a young boy. Not sure you would get ethical approval for this now, just doing that kind of thing. He had a bit of a reaction and felt unwell for several days and then made a full recovery. And then 2 months later, he definitely wouldn't get an ethical approval for this. It infected him with human smallpox, using a smallpox sore from a human to test his resistance, and he remained healthy. Okay, so this is also an important aspect of any infectious disease. Related infectious diseases can confer cross immunity. Okay, so this is a big thing with, say, something like influenza or COVID-19. There's a certain degree of cross immunity between different strains or different variants. So this was the first sort of real good example of vaccination. And then in the early to mid 20th century, we saw like a massive explosion of different vaccines being developed. Things like yellow fever, flu, influenza, pertussis or whooping cough, which is a childhood disease, polio as well. Polio, I don't know if you've ever seen, who's seen the iron lungs of Pope? Does anyone know what the iron lungs were? Any idea?
Like the device that would be like connected to each other.
Yeah, exactly. So they would be affecting the air pressure to essentially. But polio was we don't think of it now because we have all of these vaccines, right? But that was a massive cause of childhood morbidity and mortality. And then smallpox as well. Smallpox is not something we think about now, but a huge cause of mortality. So with these like massive explosion in the early 20th century of vaccines, and the World Health Organization announced a program to eradicate smallpox in the 1960s. And then in 1980, it was declared eradicated. So a bit of terminology here. Eradication essentially means global elimination, whereas elimination is a local removal or prevention of any cases. So if you've not experienced any cases in a country for a time period, you'd say that measles or polio is eliminated perhaps, and then when it's gone from everywhere in the world for a period of time, it's classed as being eradicated. And today, this is the only example where an infectious disease of humans has been eradicated. If you look at data, the data was pretty shaky at the time. These are reported cases, but actual cases were probably at least 10-fold, if not 100-fold higher. But the vaccine was introduced somewhere around here, and then we're pretty clear that it's gone fairly soon after. It was already trending down because of the various control efforts prior to that, but this was the key difference. Okay, so let's start thinking about some models. And we're going to start by thinking about pediatric vaccination. So like I said, there's different types of vaccination programs that we can have. One of the common things that we have is childhood vaccinations. Okay, so there's usually a vaccination program against things like measles, mumps, rubella, pertussis, and polio are examples. And one of the reasons that these are childhood infections is because they have a very high R0. So we're not going to cover it in this course, but there's a link between R0 and the average age of first infection. So the higher R0 something has, the more likely you are to come into contact with it earlier in your life, assuming it's sort of spreading in the population. If it's very rare in the population, then no. But if you have an epidemic of something, or if it's endemic in the population at a reasonable level, the higher the R0, the more likely you are to come into contact with it at a young age. So even if some of these infections you don't necessarily have severe symptoms at a young age, we usually vaccinate at a very young age in order to try to keep that prevalence down. One of the offshoots of some of the modeling, again, we're not going to have time to go into this in this course, but a really good example of where modeling helped shape public interventions for vaccines was with rubella. So rubella causes kind of like flu-like symptoms in young children. It's only really a problem for women of childbearing age because you can get rubella congenital syndrome, so that can affect the fetus. One of the things with vaccines is that when you start vaccinating the population, you're reducing the effective reproduction number, which acts to increase the average age of first infection. So with something like rubella, you need to make sure that you vaccinate the population really well to reduce the prevalence. Because if you just do a little bit of vaccination, you can increase the average age of first infection to when it starts causing problems to women of childbearing age. So this was one area where modeling was used to basically say, look, we need to kind of, you're almost better doing nothing or doing a lot, and doing a little bit can actually be worse. Okay, so like I said, we won't get a chance to go into that, but I just wanted to highlight it as an example, like a real practical use of where modeling has informed public health policy with regards to vaccination. Okay, so let's think about our SIR model, and we're going to start by vaccinating a fraction P of individuals entering the susceptible population at birth. Okay, so from now on, I'm going to be, unless otherwise stated, I'm just going to be referring to any of these models, SIR or SIS and so on, as the proportion of individuals in each of those classes rather than the density. Okay, so these have already been rescaled according to population size. Okay, so change my susceptible population. We're going to have a birth rate B. We would be multiplying by the population size, but this is because this is going to be 1, because we've rescaled according to proportions. There is no N in here. That disappears. And we're going to say we're going to be vaccinating a proportion P of those individuals. So 1 minus P times by our birth rate are going to be the rate at which individuals are coming into this susceptible class. We're going to assume density-dependent transmission, so our standard transmission term beta SI, and then a natural mortality rate not related to disease of B times by S. So we're using the same birth and death rates here because this helps keep a constant population size. And over reasonably short time frames, things like human populations, these are relatively okay, or at least in many countries. Okay. Our infectious class, DIDT, is going to be beta SI minus our recovery rate, gamma times by I. I'm going to assume here as well, for simplicity, that we're not going to have any disease-associated deaths or that they're negligible, okay? Just because this helps keep the constant population size a bit easier to manage. Again, we have a natural mortality rate here for the infected class. And then DRDT, we have those individuals who recover. We're assuming they become perfectly immune. We have those individuals who are vaccinated. So at each unit time, we're introducing B new individuals into the population through births. And a proportion 1 minus P are going to be susceptible, and a proportion P are going to be vaccinated and immune. Okay, so they go straight into this R class. And then we have minus B times by R, where B is our, we've got equal birth and death rates here, so this is our death rate of our recovered individuals. Okay, so all of our parameters are as before, and just a reminder, S plus I plus R here is going to equal 1. These are all proportions. So one thing I can do with this quickly is I can just look at my R0. So to work out my R0, when S is approximately equal to 1, so when all of the population is susceptible, if I look at the per capita growth rate of my infectious class, this is going to equal beta minus gamma minus B. So I've divided through by I, and this S is now equal to 1. And this is positive. In other words, we get an epidemic when my R0 is greater than 1. So if I rearrange this, If I take my gamma and beta over to the other side and then divide through by them, I'll get beta over gamma minus b must be greater than 1. So this is my R naught for this model here. Sorry, beta gamma plus b, that should be. The other way of thinking about this, remember, is there's a couple of different ways in which we can find our R naught here. We can think about the average rate of new infections for one infected individual, which would just be beta, divided by the time, or divided by the rate at which we lose infections, or otherwise multiplied by the average infectious period. The average infectious period is going to be 1 over our loss terms in this class. Okay, any questions so far? Okay, so we've got this model of pediatric vaccination. We want to think about what proportion of the population needs to be vaccinated to prevent an epidemic. So I'll work through this one with you guys. In other words, what we want to do is we want to find when our effective reproduction number, which I call RE, is less than 1. Okay, so let's think about our disease-free equilibrium, which I'll refer to as DFE. In other words, this is when I is equal to 0. The reason we're going to look at the disease-free equilibrium is because we want to essentially look at the stability of that disease-free equilibrium. So if we write down our equations dsdt and drdt in the absence of our infectious disease, so when I is equal to 0, just going to copy down the equations above, but everywhere there was an I, it's just going to go to 0 now. So you have b times by 1 minus p. With no infection term, the beta SI has disappeared, so we just have a minus bs. And the rdt is going to be b times by b minus r. The recovery term has obviously disappeared now. Now, if you solve those, it'll be relatively easy to see from this second equation here, the rdt is only going to be equal to 0 when r is equal to p. So you can say r star is equal to p. And because these are proportions, when I is equal to 0, s plus I plus r must equal 1. So s star must equal 1 minus p. So my disease-free equilibrium in this model, when I is equal to 0, we have a proportion 1 minus p of the population is unvaccinated and a proportion p is vaccinated. That shouldn't be too surprising given that p is the proportion I'm vaccinating at birth. Okay. The question then is, when is this stable? Now, we don't actually have to look at our Jacobian and everything here, because if this is stable, then my per capita growth rate of my infectious disease, DIDT, divided by I, which in this case is going to be beta times by S star minus gamma minus B, has to be negative. Okay, so all I've done here is I've solved this model and the equilibrium disease-free equilibrium when I is equal to 0. So it eliminates this equation and these terms here. That gives me a value for S star and R star at my disease-free equilibrium. And now I'm going to say, okay, given that I'm at that disease-free equilibrium, when does this equation grow? When I is very, very small. Okay, so what is its per capita growth rate? If this per capita growth rate is positive, then this must be unstable because we're moving away from it. If it's negative, then this is going to decay to 0, so we just end up straight back at our S star and R star. Okay, back at our disease-free equilibrium. Okay, so when is this less than 0? Well, remember our S star is equal to 1 minus P. So we're going to have beta times by 1 minus P minus gamma minus B has to be negative. Or 1 minus P has to be less than gamma plus B over beta. Or P has to be greater than 1 minus 1 over R naught I'm using this is 1 over R naught here from the previous slide. We're rearranging this. We have to vaccinate a proportion at least 1 minus 1 over R naught. And this is referred to as PC. This is a really important finding because even in this relatively simple model, where we're assuming that everyone's homogeneous, that transmission is density dependent, and that that homogeneity means there's no differences in contact patterns or susceptibility, or anything like that. We get this relationship here between our proportion we need to vaccinate and R naught. That's all that matters. It doesn't matter if the transmission rate versus the recovery rate. All that matters is how it combines together into this R naught. So this is a very good first approximation as to how many individuals we need to vaccinate. So just to check your sketching skills, I want you to have a go at sketching what this vaccination threshold is as a function of R naught. Have a quick go at that. Okay, so if you want to sketch this function, we're going to sketch a critical vaccination threshold, PC, against R naught. So what do we know from this? Well, when R naught is equal to 1, we can have 1 minus 1 over 1, which is just 0. So I know that when R naught is equal to 1, this must be a point. This must be a point on my curve, okay? Now, actually, as I'm interested in the vaccination threshold, I'm going to not be interested in negative values. So if R naught is less than 1, no matter what we do, it's going to die out. So there is actually no vaccination threshold that's critical there. So really, this should be written in some ways as PC is equal to the max of 0 and 1 minus 1 over R naught. So this stretch between here is literally along 0. I'll forgive you if you did the negative thing here, that doesn't matter. I just asked you to sketch a curve. I didn't get you to think about what this meant here, really. Okay, what happens when R naught gets very, very large? So whenever we're sketching curves, think about intersections and think about what happens when things get very large or very small. When R naught gets very, very large, we're going to have 1 minus 1 over something very, very large. 1 over something very, very large is going to be tending towards 0. So when R naught tends towards infinity, this is going to tend towards 1. So I know that this can never be greater than 1. Also, that makes sense, right? Because we're talking about proportions. You can never vaccinate more than everyone in the population. So this will asymptote towards that value as R naught gets very, very large. Okay, so this is my curve, 1 minus 1 over R naught. Yes.
So for every vaccination model, it is very similar.
I mean, I always say every vaccine is like, obviously as more models get more complicated, then, this changes a bit. But as a first approximation from a very, very simple model, this gives you a pretty good idea as to what goes on. As you have, for example, more heterogeneity in population, we're going to talk a little bit about targeted vaccination in a moment. If you have targeted vaccination, then you can reduce your vaccination threshold if you're vaccinating a smaller at-risk population that say is disproportionately spreading the infectious disease. So, for example, if you had a vaccine against certain sexually transmitted infections and you targeted it towards sex workers, then you'll be able to reduce the threshold. Okay. But if we think about some examples here, what do we know? We've not talked about the R naught for particular examples of infectious diseases, but for influenza, it's somewhere just above 1 to 2, like usual seasonal influenza. So this is influenza. Goes up to maybe around 2. It depends obviously on population because your contact rates are part of this. But that means if you were able to vaccinate roughly 50% of the population, you would be able to eliminate influenza. But the issue with influenza, or the biggest issue with influenza, is that it evolves so rapidly. The reason that you need to have flu vaccines every year is because the flu vaccine from last year, the dominant strain last year, is very different to the one this year. So influenza is very unstable in that sense. It evolves very rapidly. And the reason it evolves rapidly is because it is unstable, but also because we build up immunity to it quickly, and then that changes things. Okay, COVID-19, the original strain was something more around here. Maybe around 60% would have been okay. The Delta variant was maybe more around there, and an R0 of maybe 8-ish. Estimates vary a little bit, but you see with COVID-19, the Delta here, maybe needs something more like 90% of the population, maybe 85 to 90%. Measles has an R0 somewhere like 12 to 18, depending on the population. So measles is all the way up here. You see, obviously, as we get towards these larger values of R0, a small variation at these large values, going from 12 to 15 doesn't really affect the vaccination threshold that much, because you're already being pushed up right against that limit. So this is something like measles. Also goes to show why it's so difficult to control measles, because it has such a high R0. That means we need to be vaccinating, 94, 95% of the population potentially, especially if the vaccines are not 100% perfect. So, just because you have a vaccine doesn't mean you're necessarily immune. That means that, if it's only effective in, say, 95% of people, you basically have to vaccinate everyone. This is why, as soon as there is any sort of vaccine scares and people sort of drop out of childhood vaccination programs, you get these outbreaks of measles, or in communities that don't typically take vaccines. So yeah, this is a relatively simple graph from a relatively simple model, but it still gives you a pretty good first estimate as to how many individuals you need to vaccinate based on just this quantity R0. Again, it doesn't matter the timing of things, whether that transmission rate is very, very fast and your recovery rate is very fast, or if it was something that was a very slow burning disease that takes, has a much longer infectious period, but also has a lower transmission rate. It all boils down to this R0 as the key thing. Okay, let's move on to targeted vaccination. These aren't the only ways in which you can vaccinate populations. You can do things like a rolling vaccination program, or you could have like there's an epidemic and you quickly respond to it. That's kind of what we'll do a little bit here. I need to talk a little bit about targeted vaccination though. So in the last lecture, that dealt with risk-structured populations where individuals varied in their risk of transmission or their contact rates. So again, individuals that maybe they could be something like service workers that come into contact with lots of people in, say a supermarket or a restaurant, or they could be, in the context of sexually transmitted infections, sex workers that have a lot of contacts, disproportionately responsible for a lot of transmission. Okay, so we're going to assume that we have a population of individuals like before that are either high or low risk of infection. We're going to assume this is based on their contact rates as well. And we're going to assume that recovery leads to full immunity. So this lecture here dealt with an SIS model. We're now going to be doing this in an SIR model because we're thinking about vaccination. What we're going to do is we're going to say, okay, suppose this vaccine is either very costly or it's impractical to vaccinate the wider population. What happens if we can target that vaccine to those high-risk individuals who disproportionately spread this infection? What proportion P do we need to vaccinate in order to prevent an epidemic? Okay, so let's think about the start of an epidemic. We're not going to have any demography in this model to make it easier. So we're just thinking about a short-term epidemic. We want to know, okay, how many individuals would we have had to vaccinate in order to prevent this? So using roughly the same structure we had before in the host heterogeneity lecture, a high-risk population of infected individuals, how does that grow approximately when everyone is initially susceptible? Well, I say everyone is initially susceptible, and then we're going to factor in the vaccine as well. Okay, so in this model, if you remember, we had transmission from high-risk individuals to other high-risk individuals, beta sub HH, as by portion of individuals who are high risk and infected, and similarly beta HL The beta ij is the transmission rate from class risk J to risk class I. So these are individuals who are in class L, so they're low risk, and they're infecting the high risk individuals. So that's the total force of infection. We multiply that by the proportion of individuals who are susceptible, SH. And then we're going to have recovery of those individuals. We're going to assume that the recovery is the same for both classes here. And then likewise for my low risk class, beta LH, I should say. So this is transmission from high risk to low risk individuals, times by the proportion at high risk, and transmission between low risk individuals, beta LL, IL. Times by individuals who are at low risk and susceptible. And then we're going to have recovery. Okay, so I have these approximation signs in there. I put them in already. The reason being is that we're going to be thinking about that disease-free equilibrium, and we're going to be vaccinating individuals right at the start before this epidemic takes off. So that means I can replace this SH and SL with just the proportion of individuals that are initially high risk or low risk and factor in the vaccination. So for my low risk class, we're assuming that a proportion NH is high risk. So initially we're going to have 1 minus NH in this low risk class. So I've got rid of my SH here. My SL, sorry. Then my SH, well, we're going to have NH of those initially, N sub H, but we're also going to be vaccinating them. So a proportion P can be vaccinated. So 1 minus P times by NH. So I've replaced my SH with NH1 times by 1 minus P, because there are initially NH individuals who are high risk and they're in the susceptible class, and we're going to instantly vaccinate a proportion P of them. So we've not got our recovered equations here, but they would be going to my recovered equations. And then we have a proportion 1 minus NH who are susceptible and low risk. Any questions about this model? No? Okay. So we're going to make some additional assumptions just to make this a little bit simpler. So we're going to assume that transmission from our low risk to high risk individuals is negligible, at least early on. So in other words, this beta LH that I have up here, this is the wrong way around. This should be beta HL. This term here will go to 0. So we're going to assume that those low risk individuals are not really infecting those high risk individuals, which is okay if we assume that this is imported initially into that high risk population and they're driving infection, okay? So it's not going to be a perfectly accurate model, but it allows us to get through the analysis a little bit quicker and easier. We can assume as well that this low risk population is unable to sustain transmission without the high risk population, okay? So if we were to eliminate this high risk population entirely, we're going to assume that this transmission term here is going to be insufficient to maintain the disease. So in other words, the R0 for just our low risk population on its own is going to be less than 1. The reason why that we're going to assume that will become clear in a moment, hopefully. We've got this assumption that proportion NH are high risk and that risk structure doesn't change and that all individuals are initially susceptible. So how do we work out our targeted vaccination threshold? Well, what we can do is we can calculate an effective reproduction number by looking at our Jacobian. So if we work out a Jacobian of those DIH and DIL DT equations above, in other words, these ones here, with this assumption that beta HL is equal to 0, then we get the following Jacobian. So we should have NH times by 1 minus P times by beta HH. So it's a transmission from high-risk individuals to other high-risk individuals, and they're lost at a rate gamma. We've set the beta HL to be equal to 0. So this top right element of our Jacobian is also going to go to 0. In the bottom left, we're going to have 1 minus NH times by beta LH. So this is infections caused by high-risk individuals infecting low-risk individuals. And then in the bottom right, we've got low-risk individuals infecting low-risk individuals. So we're going to have 1 minus NH times by beta LL, and then recovery of those individuals. Now, at the end of the last lecture, the next generation matrix was introduced as a way of solving or finding our effective reproduction number or our basic reproduction number, depending on the scenario. I've left that as a self-study here. Because we've got already a 0 in this top right term, we can read off our eigenvalues straight away. The key thing between reading off your eigenvalues and working out your reproduction number straight from your Jacobian versus the next generation matrix is that our threshold for where stability changes shifts, okay? So with our Jacobian, remember, stability changes whenever our real part of our eigenvalues goes from positive to negative or vice versa. Whereas with our next generation matrix, it's all about when our eigenvalues are above or less than 1. Okay, so it shifts everything. So just be a little bit aware of that. I'll leave that as an exercise for a self-study problem at the end for you guys to work through and check that if you did this through the next generation matrix that you get the same result. Okay, just remember the thresholds shift. Okay, so the eigenvalues here are just the diagonal elements. We have NH 1 minus P times by beta HH minus gamma. And lambda 2 is the bottom right element, 1 minus NH times by beta LL minus gamma. Okay. So an issue here is that we don't know which one of these eigenvalues is larger. Remember, our basic reproduction number or our effective reproduction number here, because we're vaccinating, depends on or is equal to the largest eigenvalue. Okay. And the reason we don't know is because we don't know whether it's, you know, the high risk or the low risk individuals who are the bigger driver of this infection. Essentially, there's one associated with each of these populations. But we assumed back up here that the low risk population is unable to sustain transmission without the high risk population. So in other words, this here is our R0 for our low risk population, and we're assuming that this is less than 1. Either because there's not enough low risk individuals or the transmission rate between them is low enough that they're not able to sustain it by itself. So we know here that lambda 2, which is our R0 low, got to be less than 1. That's nice because it means that we can just focus on our other eigenvalue. And that's where we're targeting our vaccination. So our effective reproduction number is guaranteed to be less than 1 when our first eigenvalue, lambda 1, is less than 0. Because what that's saying then is our disease-free equilibrium is going to be stable because both of these infectious classes can't grow. They'll shrink towards 0. Therefore, we won't get an outbreak. So my lambda 1, just copying that down from the previous slide, is NH times by 1 minus P times by beta HH minus gamma. Just check I copied that correctly. Yeah. And we need this to be less than 0 for our basis to prevent an epidemic. Okay. So this is just a bit of algebra now. We just need to rearrange this to get P. So if I take the gamma over to the other side and divide by NH and BHH, we're going to 1 minus P has got to be less than gamma over beta HH NH. And then a tiny bit more rearrangement here to get P. It's got to be greater than 1 minus gamma over beta HH NH. Which we can also write as 1 minus 1 over R0 for our high-risk population. In this particular example, remember this P here, this is the proportion of high-risk individuals, not the proportion of the population that we're vaccinating. So because already we're starting up with a relatively small proportion of high risk and they're key drivers, as long as we vaccinate this threshold, which you'll notice looks very, very similar to the kind of threshold that we saw before, 1 minus 1 over R naught, this type of pattern, even though, Senator, you asked about the more complicated model, we see relatively similar types of answers. The details change a little bit, but this general idea of 1 minus 1 over R naught or some variation on that often is related very closely to our vaccination threshold. One thing I'll just go back to briefly with that in mind is just going back to this figure here. I mentioned that, if you go from an R naught of 12 to an R naught of 18 or whatever, it doesn't massively affect your vaccination threshold because it's already so high anyway. That can really matter because the logistics of, say, vaccinating 90% of the population versus 95, like reaching that final 5% can be really difficult. So there are logistical challenges to it. But like at this end of the spectrum, when you've got an R naught just greater than 1, a relatively small change in R naught here, like R naught doubling here, for example, can massively change your vaccination thresholds. So either through changes in contact patterns or in the case of, say, COVID-19, we see a little bit of evolution of its transmission rate, push you up from, say, maybe an initial vaccination threshold of 60% up to 90% or above. One other thing I want to say about this threshold here, so this is the herd immunity threshold. I put up a paper that I wrote for a broader audience that should be fairly accessible if you're interested in reading more about herd immunity. This vaccination threshold is the same as the herd immunity threshold. So if you imagine you've got an epidemic, I'll just zoom in and sketch one here. So your classic epidemic curve looks something like this. If you remember, we sketched something before that looked like this, where we had your effective reproduction number as less than 1 here. Your effective sorry, got that round the wrong way. Your effective reproduction number is greater than 1 here and less than 1 on this side. And RE is equal to 1 at the top. You reach herd immunity by definition at that point. You remember what we've just looked at is trying to calculate the threshold for when RE is less than 1. In other words, when will the cases decline exponentially? Your vaccination threshold is identical to this peak here because by definition, that's when your cases start coming down. Often we think about vaccination thresholds with things like a childhood or pediatric vaccination program as preventing an outbreak. Really, it's the same thing. Given a certain number of cases in the population, what do we need to do in order to get those cases declining? Whether you build up that immunity naturally or through vaccination, you end up with the same threshold for those two things. Okay. That's it for the material for today. Does anyone have any questions about any of this stuff? Or if not, you can either go or work through the self-study problem for the last few minutes. Yes, Scott. So if we imagine in this model here, imagine we just got rid of every high-risk individual in the population, but we didn't change the contact rates at all. That's kind of like a key thing here. We just instantly removed all of those high-risk individuals, but the contact rates don't adjust. It's kind of a little bit tricky here because we're dealing with proportions rather than densities, but hopefully that makes some sense here. So if we removed all the high-risk individuals, then we would only care about growth. The epidemic would only be able to take off when there's interactions between these low-risk individuals here. So this would be, by definition, my R naught here, because if I go back to this equation, what I would essentially be doing is I'd be saying this is all going to go to 0 because there's no high-risk individuals, right? And then this also would go to 0 because there's no high-risk individuals. And so my R naught would be based on just these terms here. So that would be an R naught just if I had my low-risk population. You could do a similar thing if you just had your high-risk population. And so those kind of give us upper and lower bounds on what our R naught could be. And so we've assumed, or is it here? We assumed here that that low risk population is unable to sustain transmission, and therefore R naught was less than 1. So when we work out the eigenvalues here, because this is the second row of my Jacobian, and I set it up so that was my low risk population, this is essentially contribution. Move this as contribution to the next generation of infected individuals from interactions just between low risk individuals. So that eigenvalue there is telling me how much those low risk individuals interacting with other low risk individuals is contributing to new infections. This one up here is saying how much of interactions between high risk individuals are contributing to new infections. We also have the slight complication of this term down here, where it's high risk infecting low risk, but because we've assumed that there's no reverse movement back from low risk to high risk, we can kind of ignore that one here, because that's set to 0. Hope that answers your question, did it? Okay, cool. Any other questions? No. Okay. So like I said, the self-study problem is essentially just confirming that this answer here, this value of R naught, the vaccination threshold, sorry, with based on our effective reproduction number, not our R naught, working out this effective reproduction number and hence our vaccination threshold using the next generation matrix. So you'd start with this same Jacobian here, and then you need to separate that into 2 matrices, F and V, based on what are new infections and what are not new infections, everything else, and then use that next generation method to work out what your eigenvalues are. Remember that threshold switches and you should get the same answer. Okay, so have a little bit of a practice that. Yeah, other than that, I will see you on Wednesday.